Okay, I've had to add a little arrow up on the screen in order to give the camera something a little bit better to focus on. So here is the unaffected beam. Now we'll put the single slit in front. And there is a slit 0.16 millimeters across. I'll put a smaller slit. That is a slit 0.8 millimeters across. That slit is 0.4 millimeters across. And that slit is 0.2 millimeters across. And you can see that as we went from wider to narrower, we get a larger and larger central bright fringe. So this is the narrowest, a little bit wider, wider, and the widest. So we notice that as the slit gets wider, the fringes get narrower. Okay, very, very good. So here I've got a blown up version of two slits, two patterns. I've got a single slit pattern here and a double slit pattern above here. And for both of them, they have the same slit width. The slit width of the single slit is 0.8 millimeters. The single slit for the slit width for both slits in the double slit are 0.8 millimeters. So what I want you to notice are the similarities and the differences between these two. First of all, for the double slit pattern, we have very, very small fringes. Bright fringe, dark fringe, bright fringe, dark fringe, bright fringe, which is not reproduced in the single slit pattern. That's because that pattern is formed by the two slits interfering with each other. We only have one slit, so we cannot have the two slits interfering with each other. So the very small pattern, bright, dark, bright, dark, bright, dark, that is caused by the double slit interference. Now, the single slit interference pattern, I want you to notice, is actually overlapped onto the double slit pattern. So while these central bright fringes are bright, they get dimmer over here and dimmer over here. Then they get brighter again, and then dimmer here and dimmer here, and that is being caused by the single slit interference, or single slit diffraction. So the double slit is made of two single slits. So the double slit pattern is actually a combination of double slit interference and single slit diffraction. So these fringes, bright, dark, that's caused by the double slit interference. But the bright section here, and then dimmer here, brighter here, dimmer here, darker, brighter, darker, brighter, that's caused by the single slit diffraction. So even with the double slit pattern, we still have single slit diffraction going on. Very, very good. Okay, so far for the single slit and the double slit patterns, we're taking our round beam and cutting off parts of it on the side, cutting off two edges for the single slit or cutting off parts like this for the double slit. Well, what if we were to basically cut out all of the tails? So basically cut out all of this outside part and only allow the central part of the beam to pass through. We might expect it to spread out in all directions. Well, that is exactly what happens, and that is what we get when we pass a laser through a round aperture. So let's see what happens. Let's actually do that and see what happens, and then we'll talk about why we get that. Okay, now I know it's a little bit hard for the camera to focus on this. I think I need to kind of keep my hand up here to give the camera something to steady on. What you notice is we get a circular pattern with a bright spot in the center, and hopefully you can see this. There is a dark fringe, a dark circular fringe surrounding it, and then a bright fringe surrounding that, and then a dark fringe surrounding that. So we get a circular pattern of fringes. Now what I want to focus on, so to speak, is this central bright fringe. We'll say that the size of the central bright fringe is determined by the center of that dark fringe that surrounds it. So the size of the bright fringe will determine by how big that dark fringe is surrounding it. Okay, great. So For our round aperture, and we'll assume we have some round aperture with diameter d, again, we'll define this central axis, okay, like that. And then what we get on the screen is a pattern that looks something like this. We get this bright, round, bright fringe in the center, surrounded by a dark fringe, and then surrounded by another ring of a bright fringe, surrounded by a ring of a dark fringe, etc., etc. Now, what I want to focus on is how large is this central bright fringe, and we'll define that basically by the angle formed to the center of the dark fringe. So, what is that angle from the central axis to the center of that dark fringe? Well, for all the others, for the double slit, we ended up with equations like little d sine theta was equal to m lambda, or m plus a half lambda. For the single slit, we had w sine theta was equal to m lambda. Well, we might expect something similar here, but it's almost the same, but not quite, because in this case, if we were to look at the rays going in different angles, for the double slit, we always had the same amount of light coming through the two slits. For the single slit, we had the same amount of light coming out the top, the middle, the bottom, 1/3 down, 2/3 down. It was always the same amount of light. In this case, we'll have, say, a lot of light coming through the middle of the slit, but as we go up or down, there's less light because the opening is round. There's very little light coming out the very top, very little light coming out the very bottom, and more light as you go towards the center of the slit. So the analysis is quite a bit more complicated. So I'm just going to give you the result. It turns out the angle that gives us the location of the center of that first dark fringe is d sine theta is equal to something times lambda, but it's that something that's a little bit more complicated. That first dark fringe is not when this quantity is 1, but it's actually 1.22. I'm not going to go through that analysis. I'll leave it at like that. It's gone through in some textbooks, typically not our 11-12 textbook, but maybe something like a 22-12 textbook, but I'll just leave it at that. It's d sine theta equals 1.22 lambda, or sine theta is 1.22 lambda divided by d. Let's try to apply this to a particular kind of problem. Remember, this is what happens, this is what we get when we have a source of light coming through a round aperture. It creates this diffraction pattern. Now let's imagine we have, rather than two openings, let's imagine we have two sources. So over here, let's imagine we've got two sources of light. Maybe this is, say, two stars in the sky, for example. So we've got these two stars giving off light. They both have light coming through this same aperture. Now, this aperture maybe is the pupil of your eye, or perhaps it's the round aperture of a telescope. What's going to happen? Well, each source is going to create its own interference pattern. We'll get, let's say, one spot over here, one spot over here, and I'm imagining we're looking at the central bright fringes. Remember, each of these are surrounded by dark fringes. Now, my question is, how close can these two patterns be to each other and still be distinguished as two separate objects? Let me explain a little bit. Have you ever noticed that when you're driving on the highway, maybe at night sometime, and you're on a very long stretch of a straight road, and you see something coming towards you from the opposite side in the opposite lane, and if it's very, very far away, you just see a single light coming towards you. But as it gets closer, that single light starts to break, separate into two parts until finally, if it's a car and it gets close enough to you, you can actually see its headlights as two separate lights. But when it was very, very far away, those two lights seemed to blend together to make a single source of light. Well, what's happening is, as that light from the two sources passes through the pupil of your eye, what happens when the light hits the back of your retina is the interference pattern, the diffraction pattern, spreads that light out into fringes, two fringes, and if those fringes overlap too much, you can actually not see them as two separate sources. So the question is, how close can two sources be to each other and still be able to distinguish them as two sources as opposed to one source? Well, the criterion that we'll use is called the Rayleigh criterion. Let me put that up on the board. If the two sources are far apart, the fringes that we see are actually far enough apart that we can distinguish those as two separate sources. There's no problem in seeing those as two separate things. But as they get closer together and as those central bright fringes start to overlap, if they are so close that the center of one bright fringe is closer than the surrounding dark fringe around the other bright fringe. Now remember, how do we distinguish how big the central bright fringe is? The central bright fringe, we will say, is as large as it goes to the center of the dark fringe surrounding it. So this bright fringe, we'll say, is this big. Remember, this is actually going to kind of taper off and get dimmer and dimmer. It doesn't have bright, sharp edges like this. And this fringe will be as bright as the distance, or is as large as the distance between the two dark fringes surrounding it. Now, if we were to bring these so close that this dark fringe from this bright fringe gets to the center of that bright fringe, we'll actually see something that looks like this. We'll just barely be able to distinguish that as two objects. If these were further apart, very easy to distinguish them. If they were closer, they would overlap so much that we really couldn't tell that we had two sources. It would look just like a single blob, so to speak. So the closest that these two sources can be is when the center of one overlaps the first dark fringe of the other. Well, what is that angle? What's the angle between those two? Well, that's exactly the angle that we just said before. The angle from the center to the first dark fringe corresponds to the sine of theta is equal to 1.22 lambda over the diameter of the aperture. This is the Rayleigh criterion. That is as close, in other words, that's the minimum angle that the two objects can be and still be able to distinguish them as two separate objects. Now, this can be used in all sorts of situations. It can be used with the naked eye if you're talking about the size of the pupil of your eye. How close can two things be, say, and you're trying to distinguish them as two objects? If you can, how well can you resolve things? So you might think of this as the resolving limit. How close can two things be and still be able to resolve them? With the naked eye, if you're looking at something, how accurately can you see something and distinguish it as two objects? Or with a telescope, if you're looking at something through an aperture of a telescope, the size of that telescope will limit the resolving power. How clearly can you see something? Let's stick some numbers in here and maybe it'll make a little bit more sense. Let's imagine that you're standing over here and you've got a friend standing over there. And you're looking at your friend with, let's just say, one eye, and the pupil of your eye has a diameter of 2.5 millimeters. And your friend is asking you, how many fingers do I have up? So your friend is actually holding two fingers. And, well, so here's your friend over here, two fingers. Your friend is holding two fingers, and let's say they're 1 inch apart. In other words, 2.54. So from here to here, the distance between them is 2.54 centimeters. And your friend is asking you if you can see this as two fingers, or can you only see them kind of overlapping as one finger? So can you distinguish them or not? To determine this, we'll use the Rayleigh Criterion. Now remember, for the Rayleigh Criterion, the smallest angle that can be distinguished between two things is given by sine of theta min is equal to 1.22 lambda over d. Now lambda is the wavelength of light that you're looking at this object. Well, obviously you're looking at it in visible light. Let's say we use a wavelength kind of in the middle of visible light. Let's say that lambda is, say, 600 nanometers. In other words, 600 times 10 to the minus 9th meters. D, that's the diameter of the aperture. In other words, that's the diameter of the pupil of your eye. So we'll have sine of theta min is 1.22 times the wavelength, 600 times 10 to the minus 9th meters, divided by the diameter of the aperture, 2.5 millimeters, 2.5 times 10 to the minus 3 meters. Divide that out, take the inverse sine, and what we find is that theta min is equal to 0.017 degrees. I've kept 2 sig figs because you only had 2 sig figs here for the diameter of your eye. Now, if that person, your friend, if the object is 2.54 centimeters apart, well, we have a triangle here. And we're looking for what's this distance L. If this distance over here is 2.54 centimeters, we have the tangent of theta is equal to the opposite over adjacent. So L will be 2.54 centimeters divided by the sine of our angle. And what we find is that L is equal to about 87 meters. In other words, about 280 feet, which is almost 300 feet, which is the length of a football field. So the idea is that your friend would have to be closer than the distance of a football field, a little bit closer than that even, for you to be able to distinguish him or her as holding up 2 fingers as opposed to 1 finger. That is, assuming the pupil of your eye is 2.5 millimeters. If the diameter is larger, you actually can distinguish closer things, because remember, a larger d means a smaller theta. You can resolve things at a smaller angle if the aperture is larger. Very, very good. I'd like to actually give you an example, an astronomical example of a very, very interesting situation. This is a particular star that's in the constellation of Lyra. It's called Epsilon Lyra. Now I'm actually going to move the camera back a little bit to show you what I'm talking about. So here I have a drawing of the star Epsilon Lyra, and I hope you can see it. Maybe it looks just like a little dot. Well, that's probably what it's supposed to look like. What I want to do is I want to bring you in a little bit closer and see if you can see it a little bit better. Now, I've brought you into about half the distance you were before, so this should be maybe twice as big. You can see it right there. Do you see the spot right there? Still? What does it look like to you? Well, let's bring you in a little bit closer. Here we go. Can you see it right there? Now, from that distance, you might just barely be able to see 2 spots rather than 1 spot. Let me bring you back to where you were, and I'll actually put this up on the overhead. There we go. I think you can definitely see those 2 spots there. But what I'm going to do is, let's enlarge this on the overhead. And Epsilon Lyra, it turns out, is actually 4 stars. If you look at Epsilon Lyra with the naked eye, it looks just like a single spot in the sky, a single star. If you look at it with a small telescope, you can actually distinguish this, and it looks like 2 different stars. But with a larger telescope, you can actually resolve it into all 4 stars. This is the famous double-double, or one of the famous double-doubles, the most famous double-double, where these 2 stars are actually in orbit around each other, these 2 stars are orbit around each other, and these 2 pairs orbit the other pair. So they're actually 4 stars. But you cannot resolve them, all 4, with the naked eye, and you can only resolve 2 to each pair with a small telescope, but with a large telescope, with a larger D, a larger aperture, you can actually resolve them into all 4 stars. Great. Okay, well that's it for our diffraction and interference. Hope you enjoyed that. We'll see you next time.